In this video lesson, we're going to cover example number 2, just another example of using our energy equations. Let's read this scenario. A 3-kilogram rock is pushed down with a force of 5 newtons on a spring that compresses 0.42 meters. Once let go, the rock is shot upward. At what height will the rock be moving when it's 0.5 meters per second? Be sure to draw the bar charts before you begin. All right, so let's imagine this scenario. You have on this spring, compressing it, a rock. And what are we told about this initial scenario? Well, we're told that the rock is 3 kilograms. We're told the spring is compressed or has a delta X of 0.42 meters. And we're told that in addition to all of that, there is a 5 Newton force that's being pushed down. Then what happens is the spring is allowed to reform, or in other words, expand back out, and the rock is going to be shot upwards in the air. And we want to know when the rock is moving 0.5 meters per second upwards, which that's why it's positive, what is this height? Okay, so we have a lot of different types of energies coming into play. We have, in the initial situation, we have no EG because we're going to take our spring as our reference level. So EG will come once the rock goes up in the air. So there's no EG. The rock is not moving initially, so there's no kinetic. So we're all elastic at the very beginning. So I'm going to go ahead and draw my bar chart showing all of my energy is elastic. And that's 7 squares up. Then my second bar chart is going to refer to the point at which the rock is moving 0.5 meters per second. At that point, the rock, we're assuming, is up in the air since it asks us at what height. So it's going to have some EG. The rock is moving. It tells us it has a velocity, so it has kinetic. And when the rock is in the air, the spring has been allowed to reform back to its original state. So there's no elastic. And since all of this is being done in the air, we don't have any friction because we always will ignore air resistance since it's too small to make a difference. So in my second bar chart, I have a mix of EG and EK. Now, without doing any calculating, I don't know which one's higher, but let's go ahead and just make a guess for now. Let's say most of it's EG, and then only a little bit is EK. Well, we at least want to get some bar charts in there so we have an idea, and we want to make sure that they equal the E elastic. All right, just like the last problem, I want to first figure out, if I can, what is my total mechanical energy. And I'm going to try to get that from my first bar chart. Okay, so in the first bar chart, all the energy is elastic. So that's 1/2 kx squared. We know what the x is. We're told that the spring is pushed in 0.42 meters. And so that's what would get squared. But notice it does not give me my k constant. Nowhere in the problem does it tell me that. However, we are given enough information to where we can figure out what the k constant is. Let's remind ourselves, what is a k constant? The k constant is how much force is necessary to displace the spring a certain amount. So we think about k is equal to the force that's pushing the spring or stretching it a certain amount of meters. Now we know that the amount of meters is 0.42. But how much force was necessary to push that spring 0.42 meters? You may be quick to say that it was 5 newtons, but be careful. The force of 5 newtons was not the only force pushing down on the spring. You had the 5 newtons, but then you also had the actual gravity force of the rock itself. So 3 times 10 will give you 30 newtons of force. So the 30 newtons of gravity force from the rock plus the additional 5 newtons of whatever's pushing gives me a total force of 35 newtons pushing down on the spring. If I take that force of 35 newtons and I divide it by the displacement of 0.42, we end up getting a spring constant of 83.3 repeating newtons per meter. So that's what I'm going to plug in here. And now I can figure out what my elastic energy is, and therefore what is my total mechanical energy. So 83.3 times 0.5 times 0.42 squared ends up getting me an elastic energy of 7.35 joules, which is also my total mechanical energy of 7.35 joules. What this means is that the energy has to be conserved, and therefore it always has to be 7.35 joules no matter where. So in the second bar chart, my gravitational and kinetic energies together must equal 7.35. Okay, out of those two energies, which energy could we calculate? Eg or Ek? Well, we know the mass for both of them. The mass is the rock, so that's not going to depict it. But instead, it's going to be the height or the velocity. To calculate Eg, you need to know what the height is, which we don't. To calculate Ek, you need to know what the velocity is, which we do know. It's 0.5 meters per second. So let's do that now. My kinetic energy is going to be 1/2 the mass, which is 3 kilograms, times the velocity, 0.5, squared. If I take the mass, 3 times 0.5, and multiply that by 0.5 squared, I end up getting my energy is 0.375 joules. If I compare that to the total energy, that's pretty small, which tells me a majority of the energy at this point is going to be Eg. And so to find my Eg, I'm just going to take my mechanical energy, total, minus my kinetic energy, which 7.35 minus 0.375 gives me 6.975 joules of gravitational energy. Now I can use this to solve for what the height is. Because remember, gravitational energy is mass, which is the 3 kilogram rock, times the gravitational acceleration, which is 10, times h. H is what we are going to solve for. So we take 6.975 divided by 3 and divided by 10 to get a height of 0.2325 meters. This concludes the video on example 2 involving energies.